Okay. As people stream in, I'd like to welcome everybody to the afternoon session of the first day of real-world cryptography. This session will be focused on secure communications, and there's some great talks coming up. So first, let's see, the doors are close to closed. I hear quiet going over the room. All right, we're all ready. Okay, so first I'd like to it's my pleasure to welcome Nadim Kobesi, who's going to talk about Noise Explorer. Nadim?
Hello? Is this on? Can you hear me? La 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 la. Okay, great, awesome. Well, thank you very much for being here, and thank you for giving me this great opportunity to talk about my research, which I really care about and I really hope is useful to you all. So thank you. Thank you very much. This is joint work with my thesis advisor, Kartik Bhargavan, who is here here in the audience, potentially against his will. No one knows. We'll find out. It's called Noise Explorer, the fully automated modeling, analysis, and verification for arbitrary noise protocols. So noise protocols, that's a bit misleading. When you first hear that, you'll think there are protocols called noise protocol, but that's not necessarily true, because noise is actually a protocol framework, which is a framework for secure channel protocols, not disk encryption protocols or anything like that. So noise is actually a framework for designing crypto protocols. They're based on Diffie-Hellman key agreement. They kind of maybe look a little bit like something like TLS, like any other secure channel system, but they're not TLS. And the most interesting part of noise is actually the fact that the framework, the noise protocol framework, has a simple language for describing the messages within the noise protocol. And from that language, which looks, by the way, something like that, see on the right. So that's a full noise handshake pattern, which is essentially a noise protocol. From that description, you have the complex state transformations, which are specified in the noise specification. And they essentially say, well, this token's here, we're going to have that transcript hash mixed in, and so on. So all of these rules contained in the noise spec kick in, and then you get a whole secure channel protocol thing, which is really cool. Now, the author of noise is Trevor Perrin. This is Trevor Perrin. And he gave an excellent talk about noise last year here at Real World Crypto 2018. It was held in Zurich. So please check out his talk. He created noise. I did not make noise. Except for now, I'm certainly making a lot of noise. Thanks, Ben. That was a great joke. My friend Ben told me this joke. And so, yeah, it's on YouTube. And the link is on the screen. And it's no longer on. OK, all right. So let's try to understand the notation of noise. So you have this thing on the right, which says IK. And if I can, OK. So this is like the name of it. And then you have these tokens. So if you have an arrow going from left to right, it means that the initiator, or Alice, is sending a message to Bob, the responder. If you have an arrow going from right to left, it means that the responder, Bob, is replying to the initiator, Alice. And when you have these ellipses, 3 dots, it means that whatever happened before actually happened before the session started and people started talking and the protocol was live. So if you have this thing here, like an S token, this is like before the protocol started, Bob sent his long-term static prekey, maybe, for example, to Alice. And when the protocol started, Alice sent a public ephemeral key to Bob. And she also did, for example, a Diffie-Hellman shared secret derivation using her private ephemeral key and Bob's public static key, and so on and so forth. And so every one of these arrows, especially only after the ellipses, actually also could contain a payload, and which is like a message, a photo, whatever. And these payloads are opportunistically encrypted as well. So once we have shared secret agreement, encryption on certain payload elements kicks in automatically. Now, as I said, this is a really simple language, right? So noise tries to be secure by default. It tries to be mistake-proof. And so a lot of the operations within noise, the cryptographic operations like encrypt and hash or HKDF, the state objects like cipher state, symmetric state, handshake state, and by the way, each of these is contained within the one coming after it. Or the actual state transformations are all defined in the spec, and there's a bunch of rules that says, well, oh, if a E token comes after a whatever token in that position, well, then you need to do a mix hash. And so if you actually implement things according to those rules, you are supposed to end up with a secure channel protocol that does the best it can with the amount of keys available to it according to what you yourself wrote here, right? And so that is the goal of noise. Now, noise is used in many cool applications, such as WhatsApp. Have you heard of it? People use it. And so it uses noise. And also WireGuard, which is a cool new open source project by Jason Donenfeld. You should check it out. It's an open source project. It's a VPN. It also uses noise. And so now, noise, as I said earlier in my talk, is a protocol framework. There's not, like in TLS, you have a single protocol. It's called TLS. In Signal protocol, you have a single protocol. It's called the Signal protocol. In noise, there is no such thing. There's a million protocols. There's an unbounded number of noise protocols. And so the noise authors knew this, of course, and they developed a grade-based system for trying to understand the security goals and what exactly each noise handshake pattern achieves at which potential message in terms of authentication and also in terms of confidentiality. So there's 3 authentication grades. We expand these to 5 in our analysis, but that's not important. And there's 6 confidentiality grades. There's also something called identity hiding, because noise actually will also encrypt your long-term identity key or static key opportunistically. And so identity hiding is whether it will reveal to an observer your identity key or not. We don't analyze that, but it's important because the noise spec certainly talks about it. So in terms of authentication grades, you can start with level 0, which is just no authentication. This payload may have been sent by any party, including an active attacker. And so here, this message has a 0 authentication grade. And you can go all the way up to 2, which is that assuming the corresponding private keys are secure, this authentication cannot be forged. With confidentiality, you can start with 0, which means that this payload is sent in clear text. And you can go all the way up to 5, which means strong forward secrecy, assuming the ephemeral private keys are secure and that, of course, the recipient is not being actively impersonated in the middle of the session. Then this payload just simply cannot be encrypted. And you have a lot of weak forward secrecy stuff in between. So for example, this last message, which by the way has no tokens, which means it's just a payload message. There's no fancy Diffie-Hellman stuff. I just spotted Mr. Whitfield Diffie while saying that. What a coincidence. Sorry. I am very nervous at the moment and therefore saying things that I shouldn't be saying. I don't know whether you've noticed that physiological effect that I'm exhibiting at the, all right. So there are so many security goals, 50 plus handshake patterns in the spec alone. So how do we verify all of these protocols against these security goals? I mean, if you just look at the noise spec alone, you'll see that there's about 60 or 55 noise handshake patterns defined in the spec. So if we have a security query like trying to verify something based on every one of these, then that's like 500 security queries that we're going to have to manually prove, right? Because we're cryptographers, want to be rigorous, want to prove everything. And so that's a lot of them. You're going to spend a lot of time. You're not going to see the world. You're not going to visit Japan. It's going to be a problem. And so noise also, let's not forget one of the more important parts of noise, which is that it allows for use case specific protocols. So maybe TLS shouldn't be the answer to everything. Maybe you have a use case where you can't really obtain the keys at the right time. You can't obtain a certificate at all. You can't do some of the stuff that TLS requires, or you just want something more streamlined. And noise really allows you to do this because it allows you to design your own protocol that can really fit your use case. So how can we ascertain in this even more interesting context which security promise any noise handshake pattern can give, right? Especially if you want people to design their own. What an interesting problem. Well, introducing for the first time in the United States, Noise Explorer. Wow, it's amazing. It allows you to verify any noise handshake pattern. How does it do that? There's an unbounded number of them. Well, you can design noise protocols and immediately obtain 2-spec validity checks and helpful visualizations. Pictures, everyone likes that. You can generate models for formal verification. Now, this is the more interesting part. So you can enter any description for any noise protocol pattern, noise handshake pattern, and you can immediately from there obtain a formal verification model, and you can just get the answer to the security queries. Does this achieve authentication security grade 1, 2, 3, 4? Does this achieve confidentiality grade 1, 2, 3, 4, 5? Immediately. Well, after running the formal verification model, which in many cases is not very immediate, but you get the point. And these are run with top-level processes with the security goals already generated, and also in a very ambitious model that includes a compromise principle, right? I'll get to what that means in a bit. And you also have, because some of these models take a very long time, you have a noise explorer compendium. So I've already run a lot of these models, and there's a compendium that shows you the results for the models that were run. And this is very new, announcing today for the first time. Very soon you'll be able to generate implementations. So Noise Explorer will also, you just enter the noise protocol handshake description, which is just the little things I put on the right earlier. And from there, you will immediately obtain a full implementation. I'm almost done. I'm just doing interop testing on the JavaScript part now, but I'm also going to do Go. And other languages could be there. I didn't pick these two languages I just know them well and use them a lot. But it could do C++, Swift, Java. It's fine. Any language, really, in the future. This is all open source software. You can all contribute to it. You're most welcome. But what is formal verification with ProVerif? So I studied in Europe. In North America, formal verification is, maybe I'm wrong, but it's not as well known in my experience. And so automated formal verification essentially is an approach to beat this thing that's happening a lot in applied crypto, which is to code first and specify later, if ever, right? A lot of crypto systems, if you look at the history and evolution of TLS, so TLS 1.0, 1.2, 1.1, people really were being very pragmatic about it. And then there were a lot of attacks, drown, smack, freak, whatever, and poodle, and all of those attacks. And so in TLS 1.3, the formal verification and there was a lot more academic involvement. And so people are moving towards a specify first and code after methodology, which maybe is more fruitful. Now, there are two main models for formal verification. You got the symbolic model and computational model. I'm not going to get into those a lot, other than to say that we're using the symbolic model, where essentially it's fully automated. The computational model acts as a proof assistant a lot of the time. And we can model protocol flows and try to find contradictions to security queries. So we model the flow of the protocol. We say, all right, well, the IK noise pattern is going to be executed between Alice, who's talking to Bob and Charlie, Bob, who's responding to Alice and Charlie, and by the way, Charlie's fully compromised and controlled by the attacker. And there's an unbounded number of messages and an unbounded number of sessions. So what are the security goals that are accomplished in that setting? And then we ask, well, we formalize what authentication 1 means and what authentication 4 means and so on. And we say, well, which one of these are going to be met? So that's what we're trying to do. And we're trying to do that with ProVerif, which is the tool for symbolic automated formal verification developed at INRIA in Paris, where I did my PhD with, it's developed by Bruno Blanchet and his team. You can check it out. It's open source software at this URL. There's a very comprehensive manual also if you're interested in getting into it. And I strongly recommend you do. It's really cool stuff. So if you're looking for examples on how to use ProVerif, you can just generate a model using Noise Explorer, actually. But also, for other use cases, I recently defended my PhD, and there's many use cases on ProVerif. I did a lot of stuff with ProVerif. You can download that and check it out. So in ProVerif, actually, what's interesting in the symbolic model is that many notions of having information inside cryptographic constructions are reduced to basically symbolic elements. So essentially, all cryptographic primitives are perfect primitives. A hash function, as a matter of fact, is a perfect one-way function every time. There's no such thing as a hash function that's vulnerable to a length extension attack. At the same time, so if you look at the right here, you'll see that Diffie-Hellman expand initiation takes 2 keys and gives you a key. And actually, if you have G to the A to the B, it is equal to G to the B to the A, right? And so this is a very naive encapsulation of Diffie-Hellman, but you can kind of see how this is represented using the symbolic model, and I hope this is useful. So this is how we represent encryption. So you get a key, a nonce, a bit string, and a bit string, and you get a bit string, right? And so this is, for example, the key, the nonce, the authenticated additional associated data, and then this is the plain text, and you get for text, right? And decryption is actually a reduction of that to deconstruct it back to the plain text if the key and the nonce and the associated data all match, and then you get a Boolean that says whether the decryption was valid or not. And so, for example, this is a naive way to capture ASGCM or XChaCha Poly 1305 or any similar primitive, right? And then we essentially have a common state management library, which is written by hand and not generated using Noise Explorer, but that's it. And the rest is fully generated using Noise Explorer. And so our findings were we analyzed more than 50 noise handshake patterns taken from the noise specification itself. And we confirmed that so Trevor and his team already had numbers for many of these patterns, not all of them, but many of them. And we confirmed that these numbers were correct. So great, we were able to say formally that these predictions were correct. And we were able to offer a new verification for new patterns that are always increasing. And we essentially also showed so noise has very intricate validity rules that can sometimes, you can sometimes make subtle mistakes, and this is being worked on. But we showed that if you do make a mistake in the validity rules that are in the noise specification, then some very subtle attacks can be found. So you better have a way to follow those design rules so you don't come up with some broken or less secure noise handshake patterns, secure channels. So we also contributed some improvements to revision 34, which is currently the latest revision of the noise protocol framework. And we defined now we have more well-defined pattern validity rules to help avoid misunderstandings. And we also, of course, have higher assurance for fundamental pattern security grades based on the fact that we have all of these numbers, all of these grades being assigned, and that now, unlike before, they are related to actual formal verification, not just Trevor and his team manually for every one of them determining what is the correct grade. And we added, well, I had forgotten that number, but we added 23 deferred patterns, security grades for 23 deferred patterns. But I want to talk about something else that's very interesting. So I said that there's a new feature which is currently in beta, which is giving these JavaScript-generated noise patterns. So let's look at the advantages of that when comparing it to TLS. So Boring SSL is the TLS library that's used by Google. And and I hope this is a correct assessment, please correct me if I'm wrong. I think that if you look at the lines of code and consider only the protocol parts and the crypto parts, it comes to around this. So close to 250,000 lines of code. So maybe, Boring SSL is not optimized maybe for ultra confined small code stuff. So let's look at Bare SSL, which is supposed to be optimized, right? So Bare SSL is around 50, less than, I think 40, 30 to, I can't read the numbers here. But yeah, it's much smaller. It's less than 50,000 lines of code for the crypto and the protocol parts. However, if you look at IK, which is actually one of the more elaborate noise handshake patterns in the spec, there was supposed to be an explosion sound, but yeah, hold on. It's supposed to be like, but it doesn't do that. All right, so yeah, as you can see, and this is, by the way, a conservative estimate. I think it's going to be smaller than that, but this is about 4,000 lines of code if you include all the protocol stuff and all the crypto primitive stuff. But I'm actually, I'm giving myself a fair bit of buffer in case it turns out to be more than it actually is right now, which is smaller than this number. And so you end up with less lines of code to audit, less states that an attacker can jump to in case they find a state machine attack or a buffer overflow or similar. And that is great because it means that we can build a system that takes less trust from us in order for us to trust it. So that's good. All right, so let's do a demo. So I spoke a lot about Noise Explorer being a framework, so that means that I can demo it. So let's do that. All right, this is Noise Explorer. You can open it right now on your laptops if you go to noiseexplorer.com. So please do that if you like. And you can fully use it. So Noise Explorer is essentially, this is the title page that you'll come to. The pattern here that's already contained, and you can just type your own pattern. You can type your own, potato pattern, and you can just say, sends a static key, and then in return there's a static key, and then you're doing a static Diffie-Hellman. Aha, it says that one of the validity rules was not matched. So the validity error that it found, after an SS token, the initiator must not send a handshake payload or transport payload unless there has also been an ES token. This is one of the rules that was added to the noise specification to ensure that some properties are met. And so we can say that, all right, well, each of these is also sending an E, and then we're going to do ES. Noise handshake patterns should not contain key shares that are not subsequently used. Which ones am I? Oh, yeah, of course. There we go. And so there you get a nice illustration. You're sure that this is valid to spec. And all right, I just designed my amazing protocol. I can just click this button, and it'll download a full formal verification model that I can then run using Proverif, and it'll give me a result. I'm not going to do that right now. What I'm going to show you is the results in the compendium. So if you open the noise pattern analysis results, you can just type the name of a pattern if you've already seen it in the spec. I want to see, for example, the results for XK. All right, so I just click here. Great. These are, you can re-download the model here and rerun it if you like, but these are the results that were generated before. And so, for example, I'm interested, and you'll see that, by the way, you'll see that these results are explained using an accessible, literal style, which I really worked hard to ensure, because I think that's important. You can read it. It's English. The responder is initialized. This is all generated. I didn't write this. The responder is initialized with a pre-shared long-term static key, which is assumed to be pre-authenticated. Message A, sent by the initiator, does not benefit from sender. And so you can actually read it in a literal style. It flows well. You're not reading math formulas the whole time. But if you want to read math formulas, then be my guest, because you can just click this button for message C. You get the message over here in large numbers, large letters, and you see like, okay, well, message C. And again, this is all generated. Noise Explorer, the tool, will generate these reports for you straight out of the Proverif models once you analyze them. So none of this is written by hand. And this is useful, I think, for you to allow you to reason about this protocol that you're designing. And so message C is the third message in XK1. It is sent from the initiator. And so here you can see the actual syntax in the applied PyCalculus for the message as it's being sent, as it's represented in the Proverif model. You can see exactly how each token in the message is processed by the initiator. So you can see that, all right, well, he's calling, or she is calling, encrypt and hash. There's, if any prior Diffie-Hellman shared secret was established between the sender and the recipient, this allows the initiator to communicate their long-term identity with some degree of confidentiality. I'm referring to identity hiding here indirectly. And so you got SE, you got mixed key, you got all of these things that are being called here. And then for receiving message C, there's the same thing, the same treatment. And so you can also see exactly which authentication grades are being passed, right? So authentication grade 1, which here, like, okay, well, in the event that Bob received a message from Alice in this part of the session, and that was the message, then it must be true that Alice must have sent a message to at least someone, which could be Bob, could be Charlie, and then that someone is upgraded to, in other stages of authentication, to necessarily be Bob, right? And so that makes it achieve a higher grade of authentication. And you can see exactly what each query means, how it is written in the formal verification model, and whether it was passed or failed. And for confidentiality, you will also be able to see that well. For demonstration purposes, I wanted to be optimistic and pick something that passed everything, but you can just open any other message that is less great, like this one, which is horrible, because all we're doing was just sending an ephemeral key like that. Obviously, there's no authentication. So fail, fail, fail. You'll see also that there is no stuff, no good stuff here. All right. And that's it. That's really Noise Explorer. I'm a bit over my time. All right. So great. The future of noise, very quickly. So small use case specific protocols. The entire standard library of noise is around 1,000 lines of code, and specific handshake patterns can be smaller. As I said before, I'm really giving myself a lot of leeway and also including some crypto primitive stuff. There's a great post by David Wong that compares noise to existing work, and it's really cool because it gives you an intuition of how this stuff can be used in the wild. Even here at Real World Crypto, I've already met people who are using noise for stuff that I didn't know about. which is great. And it has the potential to be much smaller and more use case specific, have a more use case specific state machine than TLS or similar. There's upcoming work in noise. There's signatures being added that currently doesn't support signatures. There's stateful hashing and symmetric crypto, which is having an overhaul to include stateful hashing. There's something called noise socket and NLS, which is being worked on. And to be honest, I'm not particularly familiar with what that does, but you can check it out. It's related to noise. And well, that part is what is coming soon. Part of Noise Explorer, it's essentially an implementation of noise that generates implementations in JavaScript and Go. So I think that the real potential of Noise Explorer is to be the ultimate online compendium for reasoning about, designing, studying, implementing, and verifying noise handshake patterns. I want to present my special thanks to Bruno Blanchet, the creator of Proverif, and Trevor Perrin, the creator of Noise, for their assistance with this work. There's also related work. Benjamin Lip, also studying at the same lab I studied at, Prosecco in France, is working on a WireGuard automatic verification using CryptoVerif, which uses the computational model. And I also want to thank my co-author, Kartik Bhargavan, who's here in the audience and was indispensable in the creation of this work and my general higher level education in general. So please check out Noise Explorer at this URL. And this paper, and don't forget to hit subscribe and click that like button for more videos, and check, and make sure to click the bell icon for, all right. Thank you.